All right, differential operations and elimination method for systems. So this is a very unique topic going forward. It's used a little bit here and there, but its nice thing is it's a way to not dumb down, but somewhat describe what a system of equations is based off differential equations, and how to make this a little easier to look at. Let's just say instead of being y double primes, triple primes everywhere, it scales it back to kind of similar to its characteristic equation. Okay, but for now, let's just talk about how to write our notation purposes of a derivative. So far we've done all of these three going forward. Okay, but there's a different way of doing derivatives. Okay, so we're going to go back to its basic definition. So remembering y prime of t is just dy dt, right, or d dt y, right? That's another way of saying it. So y double prime means it's the derivative of this, or just two versions of this. It's d dt of y, which kind of makes sense, right? Kind of redundant. No one sees it this way, but that's basically what this represents. So what we're going to do now is instead of saying d dt all the time, we're going to denote it as just capital D. Okay? So now when we do this, this becomes dd or d squared y, or like this. And all this is saying is you're taking the derivative twice of the y value itself. Okay? Which is, basically the same thing as this happening. Again, it's just a nicer way of doing so. Okay? So what we want to do is, this way of derivatization is called the operation on the function y with differentiation operator dt. It's a big old mouthful, but basically saying is we have an operator of dt on the function y, in layman's terms. Okay. So what we can do now is we can rewrite any differential equation in terms of its operation or operator of dt. So for example, if we have this situation here, all we now is just replace all these y primes with dt, so here and here. And again, it's double because we have two of them here. Or replace it with just capital D. It makes it a lot easier to look at. Again, this is saying this is the second derivative of that portion. This is the first derivative of that. Right? And this is no derivative because this has no derivative. Right? Again, it's an alternative way to actually describe derivatives. And going forward, it makes it a little bit easier to see how are we going to solve for this, not only a derivative, but actually its implicit portion as well. Okay. So, we can also do matrix representation, which is the best part. So a little, again, precursor to linear algebra. So in matrix format, we can show the result of the operation to look like this. Okay. So if you remember matrix representations, kind of like this. Usually it's in brackets, and then these are in brackets itself to signify this is a row by column matrix itself. Okay. But that's just the operation. We're not going to go fully into operations of matrices and things like that, but it's an alternative to solve for things like this since we're going to be solving for a system as well. Okay. So the key thing is when it comes to this type of way of taking the derivatives and describing the operations, it's not always as straightforward when it comes to multiplication. So for example, if this was just x by times 1, x plus 3, we would just FOIL or a box method and we would get exactly this, right? And that's pretty much forward, and going backwards we get the operation of that. That is not always the case when it comes to operations. Sometimes the order in which things are moved does matter. Okay, so a lot of the times while you want to show this operation equals this portion, we literally have to do each one individually. Okay, now what I mean by each one individually is, well, remember, this is just an operation. We'll just call it y, for instance. So we want to show that d plus 1 times d plus 3 of some variable y gives us this portion back, where this is technically y is there, if you want to call it that. Okay, now how does this work? Is, again, we do each one individually. Again, kind of like the matrix format of old in linear algebra. We do those together first, and then we eventually do that. So here we could distribute. So this is going to be like that. Okay. Now again, what does this mean? This is the derivative and that's just itself. And now I do it one more time. Again, do the disturb property. It gives me that. Now again, going back to what it means, so this is derivative of y prime, so this is y double prime. This is derivative of y, so this is just going to be 3y prime. This is itself, and that stays itself as well. Combining like terms. And now going backwards and just rewriting this, this does give me d squared plus 4d plus 3, like that. So it does actually work out. Now again, in most cases, when it comes to operations like this, you will get that portion, but very few and very so you might not actually get it. So just you got to check when it comes to it. And again, we want to show it actually works, so we literally have to show, do we actually get that one side equals the other side. Okay. So now that we have an idea of what this represents, let's try this in a system of equations. So this is the type of stuff we can now solve using this type of operations or operators. Okay. So all we want to do is express the equations in terms of the operator of y and x. Okay. All right. So all this is saying is we would just want to convert it using just dy dx's, and that's it. So no primes or anything like that. Okay. So all we're going to do is bring all the x's and y's to one single side in both situations. So for example here, I'm just going to bring this to the other side, so I get x prime minus 3x equals, same thing on the other side, not done anything there special. Okay. And I'll do the same thing on the bottom equation. I'll just bring all the y's to one side, so that becomes this addition, and keep everything else the same on this side. Okay, now that we have this portion, our goal is to make it look kind of like this. Okay, but we do have a bit of a problem. It's equal to 0. So what I'm going to do now is, now that I have all the x's and y's, in that portion, I'm just going to first establish what these operations will look like just with these derivatives here. So this will be d minus 3 with the x. Okay. This is going to be just simply negative 4y plus 1. And we'll follow it. And you'll see what I mean by that in a little bit. Again, we want it in operation format. Same thing applies here. And now again, this is going to be 4x plus 10t. And now the last step is, because we want to set it equal to an actual number or the t value itself, I will just bring this to the other side and this to the other side, and keeping the 1 and the 10t on that side. So then finally, fully in operations of x and y will look like this. And there we go. Now, the question now becomes, well, we all have this fun stuff, what is it useful for? Okay, so the question is, how do we solve for now a system of differential equations, right? So how do we solve for x and y respectively? Okay. All right, so for that, it's actually a very lengthy process. A surprise, surprise, right? So the first thing we're going to do is we first want to create a system of 2 by 2 matrix, or system of equations of a 2 by 2. Okay. So how we're going to do that is using both equations. So for example, if we go back to our situation here, we want, in terms of just x and y, or just basically two variables. Okay. Where L1, L2 represent the derivatives with respect to t, with respect to x and y, and then f of 1 is going to be on the side. So for example, if I do this one, this will be considered my L1, this will be considered my L2, and this is my F1. And same thing applies to my second system of equations. So this will be considered L3, this will be L4, and this is F2. Okay. So that will be my new system of equations I'm going to have to be dealing with. So that's when my, basically is the first step. Make sure it's actually looking like this. Okay. Now, this is where it gets a little bit more complicated, from 2 all the way down to 4. Okay. So 2 says, eliminate one of the variables and solve to derive an equation involving x. If the system is degraded, meaning it's 0, and I'll talk about this in a little bit, then we are done, since the system will not be able to be solved and an alternate form is needed. In our case, that's probably not going to be the case because, we're learning this, right? So a lot of times it's not going to be 0, which is the best part. However, if possible, derive an equation that solves for y of t, but not derivatives. The expression for x of t and y of t are general solutions. This gets a little bit tricky. Okay, in layman's terms is we're going to solve for one of these variables using the other one, just like a normal system of equations, and then go backwards to find the other one. Okay, that's pretty much the emphasis. The problem with that is, once we find one, we have to do all that process of finding the general equation and eventually plugging it back in to find the other variable itself. That's what takes these things a lengthy to do so. Okay. Now, first I want to talk about this situation right here. Okay. Now, when it comes to solving for a system, again, right, just do it in algebraically, and the theoretical or the theory behind this is, well, if I really would just want to solve for x, for instance, right, elimination process, I would multiply top and bottom by L3 and L2, subtract, and the y's would cancel, and I get this result, right? Same thing process over here. Or you could just follow this process and, do it for you. So a little side note is if you want to eliminate the y's, okay, so this gives, or this situation here, so L1 times L4 minus L2 times L3 is what we're actually looking for, is going to be L4 times F1 minus L2 times F2. So we're just going to be using this right here. There's no need to actually do the actual process. But again, that's if you want to eliminate the y's. So if you want to eliminate the x's, it's about the same process, but you use the alternatives. So we're going to be using L1 times F2 minus L3 times F1. And I'll show you how we're going to use that in a little bit. All right, so let's actually try this process of finding a general solution to this differential equations here, right? Or the system of differential equations. So first off, I have to do step 1 is write it in this format. Okay. So again, I'm just going to rearrange a couple things to make it look a little nicer. So I'll just group all the x's and y's together in each individual case and bring all the other numbers to the other side, which is already done. So for the first equation, I'll have x double prime minus x plus y prime plus y equals -1. And I'll do the same thing on the bottom. X prime minus x plus y prime, and that is it, equals t squared. So therefore, again, I use my operation. So it's going to be d squared minus 1, the operation of x, and over here plus d plus 1 with the operation of y, and this equals to -1. On the bottom, it's going to be d minus 1 with the operation of x, and this one's just going to be d with the operation of y equals t squared. So therefore, we have our L1, L2, L2, L3, L4s, and everything else itself, F1 and F2. Okay. Oh, this is supposed to be F4 actually. So let's just write that down. So L1 will be d squared minus 1. L2 will be d plus 1. L3 is d minus 1. And L4 is just the d. And I'll just write down F1 and F2 as well. So this is step 1. Okay. Now let's go on to step 2. So step 2, let's try to eliminate the y's and see how this is going to work. So in other words, I'm going to follow this process right here. Okay. So let's go on to step 2. We're going to eliminate y. Okay, so if we do so, again, following this process I have right there, so it's going to be L1 times F1 where's F1 here? Negative 1 minus L2 times F2. Okay. Ooh, no, wait. This one's supposed to be L4. Yeah, L4. This is just D. Okay. So that is one side of it. Okay. Now I'll just do the other side. So the other side, I'll just go across, that's fine. So the other side is going to be L1 times L4 minus L2 times L3. And this is all in terms of x, since we're trying to eliminate the y's. Okay. All right, so how we do this process. So I'll talk about this side in a little bit. Let's just go on this side. It's going to be the easier of the two. So remember, now it's just taking the derivative of each one I'm multiplying, right? So the derivative of negative 1 is just going to be 0, which is nice. Okay. And now I just do the derivative of this part. Okay. So how this works again, if I distribute, so the derivative of t squared is going to be, well, with this minus 2t, and then times by 1 with the negative gives you that. So that's how we do this process here. Okay. And on the other side, I'm just going to slowly simplify this as much as I can. So this ends up being d to the third power, or I'll just do this process first, and then we'll slowly break that down. Yeah, we could do that first. So this, put that in brackets, this just gives me d squared minus 1. And if I just factor d squared minus 1 out, I'm just left with d minus 1 equal to all of this. Okay. Now, at this point, now becomes just solving at this point. Remember, because it's just now it's a differential equation. So this is go on to step 3, is actually solving. So if possible, derive an equation that solves for y of t, but not the derivative. So we did the opposite. We solve for an equation that's derived with just x of t. And then from there, find the general solution. So this is where the lengthiest comes into play, because we have no choice but to do all the other process, to get there. So which means, how do we solve for differential equation? Well, the first part, we're going to have the homogeneous part. So that's just setting the equal to 0. And the best part is already broken down to our characteristic equation, because this is the same thing now implying just r squared minus 1 times r minus 1 equals 0. So solving for r individually, we get r is equal to 1 and r is equal to negative 1. So we have a repeated root. One repeated root. So that means, again, according to our homogeneous equation in terms of the x value, this is going to be c1 e to the t plus c2 e to the negative t plus c3t e to the negative t. Oh, sorry, positive t, because it's a copy of the positive t. Okay. Again, that's just our homogeneous part, right? So now let's go to step 4. Oh, well, technically still step 3. We'll just do 3.5. Let's say 3.5. Step 3.5 is find our particular solution. Okay. All right, so our particular solution corresponds back to what it's equal to, right? So originally it was negative 2t minus t squared. Okay. So if we just break this up individually, right? So that means m is going to equal to 2. R is 0, so it's not a root. So a particular solution will look something like this. A2 e to the 0. Or if you just want to use different letters, that. Okay. Now, the question is, how do we solve for A, B, and C? This is a little odd because we have operations, for instance, right, when we are back into t values. Well, same thing applies, right? This is just second derivative and normal derivative. So what we're going to do before we do anything is we're going to rewrite this. So d squared minus 1 times d minus 1 eventually just gives this in operation format. Or that. Okay. So now on this side we just get negative 2t minus t squared, right? That's what that equals to. So what this represents is now I have to take this first, second, and third derivative, plug it into here, and eventually just solve for our variables itself, right? So taking the first derivative, c goes away. Now we just get 2at plus b. Second derivative, it gives you now just 2a. And third derivative just nicely just gives you flat out 0. So pretty much that goes away. Okay. And again, after a little bit of algebra, we end up with this. So our particular solution is going to be negative t squared minus 4t minus 6. Okay. All right, so we're not done yet, right? So we found our general solution. for x of t. So remember, our general solution is always our particular solution plus our homogeneous part. And our homogeneous part is right here. So putting those things together, we finally get one of our answers. And like I said one of the answers. Okay. Now, to get the other part of the answers, we go back to here. And now we just want to solve for y. Or in other words, eliminate the x variables, right, in such a way. Okay. So this goes back to just solving for a system, or if you want, you could just use this portion. It's going to give you the same way, so this process here will give you the same situation. But since we're going to be using a lot of just solving for systems, I'm just going to solve for a system. So in other words, I want y by itself. Okay. So it looks like you got to be careful because these are derivatives and not just normal variables. So in essence, I want just this by itself. Okay. So what that means, if I just subtract this to that, these derivatives will actually cancel away, and I'm just left with just the y, because if I distribute, it's dy, like it is here, plus just y version. So if I just, well, technically now add straight down, I end up looking like this. Or actually, it's going to be plus. Like that. And if I distribute these into the process, this ends up being a negative d and a plus 1. And again, this and this will actually cancel because it's minus x plus x. So they actually go away to just now this. And then bringing this to the other side. I now have an answer for y. And again, if I just replace this d's with the actual derivatives, this is x prime minus x double prime minus x minus 1 minus t squared. Oh, subtract it over, so minus and plus. Okay. So, unfortunately, we're not done, but we're almost done, because in this process of solving for this, you have to take the first and second derivative anyways. Or actually, worst part is you have to take the derivative here twice. Once goes here, twice goes there, and eventually collecting like terms, and then eventually we're actually done. So again, skipping a little step, just take the derivative twice. So once, twice, and then plug them in individually. Taking a long stuff, collecting like terms. A lot of stuff actually does cancel, which is nicely, especially these t's. Pretty much the whole first part goes away. And we're just left with pretty much this, because those are the only things that's left over. finally, we solve for y. So, what are my final answers? This one and that one. So if you notice, it doesn't matter which one you solve for first individually, x or y, because you will still have to go through this process anyways. You have to find the homogeneous part, find the particular part, and then eventually do the same thing for x, and you will see you actually get the same result anyway, which is actually pretty interesting. Okay? So a very, very long process how to solve for a system of differential equations, which would kind of make sense, right? You know, it's basically solving for a differential equation times 2. Right? All right, so let's try one that's not very fun to do either way. Because once we know how to solve for 2 by 2, well, that means we know to solve for any type of situations. 3 by 3, 4 by 4, eventually 5 by 5 if you want to do so, right? At some point it's redundant, but, we could technically solve for it. So that's how we're going to do this stuff here. So we want to solve for a 3 by 3 matrix, a 3 by 3 system with x, y, z. So first thing up, rewrite this into its operation form. Okay. All right, so step 1, how is this going to look like? I'll leave all the x's and y's kind of in order. So now, just like a system of equations, elimination basically means I want to eliminate a variable before I do anything else, right? So it looks like maybe z is the nice one to eliminate, just by looking at what we have, just by looking at these two here. If I add them straight down, the z's will actually just cancel away, so that's a good idea to do. So let's just try eliminating the z's. Okay. So adding straight down, so we get minus x minus 1, so it gives you basically 2. Adding these down, so this ends up being plus d minus 2 with the y. Z's go away, and this equals still 0. Okay. All right. Now, this time we have to do a little bit more finessing. Okay. So again, I want to eliminate the z's. There already is a negative here, which is kind of nice, I guess. It's negative 5 here, but we're on the right track so far. Okay. So, what should we do? Let's see. Oh, I see what we can do. What we can do is we can multiply this equation, and this is going to be a little crazy, We're going to multiply this equation by d minus 5, this entire thing, and then add it to the bottom one. I think that might work. Yeah, because everything would cancel, yeah. So think again, distribute property to that, and to this. So therefore, it's going to be outside. Literally, the whole thing will cancel away. So I will add it to down here. So let's see what's going to happen. So it's going to be this on the outside with a minus 4. So this ends up looking like a negative. Oh, that's fine. I'll put it inside. Yeah, put it inside. So this negative becomes a positive. Positive 5 minus 4 is plus 1. This becomes d right here. So this is a little tricky, so I'm just going to leave it like that for now. So, yeah. I want to do anything else. Yeah, on the outside. It'll look like that. And these will cancel, so we just get 0 now. So what does this end up looking right here? So this is just for y. So working my way here, this is going to be d squared minus 5d plus 4 with the y there. And then you could prove it earlier if you like on yourself, but this proves to be end up looking like this. I guess if you want to call it factor format, which I'm going to use it going forward. And now, finally, we have our L1, L2, L3, and L4. The nice thing is F1 is 0, and so is F2, which makes a lot of stuff much actually nicer to do. So finally, we're done with step 1. Okay. So now we're going to step 2. Okay. So since I eliminated the y's last time, I'll eliminate the x's this time just for fun. So again, just in case you forgot how to eliminate the x's, it's going to be, I guess I have it in the back of this page. Oh, right here. We'll use this template here. Okay. All right. So on one side, we'll have this process, and on the other side, we'll have that process. Okay. All right, let's write this down then. All right, so let's look up this side. So L1 times L4, so that times this. Minus L2 times L3. So that times that. I'm going to put this in the front first. And the best part is, since f1 and f2 is 0, the derivative of 0 is going to be 0, so now it's just a homogeneous. We don't have to do any non-homogeneous equations. But we still got to figure out this horribleness here, right? Now, if you really want, you could FOIL all this out and eventually, break it apart and see what this ends up looking at. Or you can kind of be a little bit deceptive. So what I mean by that is, let's just bring this here first. So if I bring that in there, this parenthesis ends up being positive d minus 1. Okay. All right, and if you noticed, we have something in common, which is kind of nice. Oh, this is supposed to be a minus as well. If I remember right, yeah, this is a minus. There we go. So we have this in common and that in common. So why don't we just factor that out, make it easier for ourselves. And what's left over? Well, this minus 1. Or plus 1 if you want to call it, but technically same thing. Yeah, plus 1. So putting this together, this whole part is already nicely factored. Which is great. This means we go back to our characteristic equation, which is the d's end up being r's. So we get r is equal to 2, 1, and 3. And the best part is it's only homogeneous because it's equal to 0 already. So we already solved for y. So our general equation for y is going to be c1 e to the 2t plus c2 e to the t plus c3 e to the 3t. There we go. Okay, so now becomes the long process as before. Now that we have this one, how do we solve for the other one? Right? How do we eliminate the other variables? Okay. So again, goes back to our situation, and now I want to get rid of y, and I want everything in terms of x. Okay. So let's just rewrite what we have so far. So actually, I'll write it in its broken down form. This is going to be fun, right? Now, this may look horrible to do, but remember, I want x as everything in terms of x. And just like last time, somehow I want y equals everything in terms of x, right? In other words, just try to get rid of it. But if you look over here, I want everything in terms of its non-derivative part of x. And if you notice, these will cancel already if I just add straight down, or just add accordingly. So that's exactly what we're going to do. Why don't we just add straight down itself? So when that happens, these will cancel. Negative 2 plus 1 gives me negative, so I get negative x. And on the other side, just everything just be added together, so I'll just rewrite that. And since I want everything in terms of x, all I'm going to do is bring all of this to the other side, which is kind of nice. Right? Okay, so if I bring that to the side, And now redoing what we did earlier, knowing that this is equal to that part down here, I'll distribute this negative to both of them. And I just collect like terms. So this becomes negative d squared. This becomes 6. Or actually, this negative. So positive 5. So becomes positive 4d. And this becomes negative. So negative 4 should be minus 2. And the last thing is, because this is negative, I want positive. Bring this whole part. It just changes the signs. Okay. And then re-breaking off the operation. That is what x is equal to. So that means take this derivative twice and then re-plug them into here, and then we're done. Again, it's homogeneous, so we don't find a particular, just call it a day. So again, taking this derivative once and then twice, plugging them into here individually, and eventually we get x is equal to this process. Okay. And unfortunately, we're not done yet because we wanted x, y, and z, but the z part is actually the easiest of them because we have everything we need just by our second equation, which is right here. We could just solve for z in that part. So z will equal to x minus y prime. Or actually, if I flip it, yeah, it's flipped. Okay. So we just plug this in for x. We already had y prime earlier. We plug that into here, and we get our solution for z as well. There we go. So that's how we solve our 3 by 3 system of differential equations.